want to tell you a story as old as the universe itself, and that's the story of life in our universe and how we're beginning to unravel it. And as with all good stories, let's start at the very beginning. Once upon a time, when our universe was very young, it was very cold and very dark. There was not a single star shining to illuminate that darkness, and there was no matter except for vast cold clouds of hydrogen and helium gas sparsely spread out into that darkness. But something remarkable happened a few 100 million years after the universe was born. Cosmically speaking, that's the blink of an eye. Those vast clouds of hydrogen and helium began to collapse under their own gravity. And the densest and heaviest of those collapsing clouds started to shine with their own light. And the first stars were born. In the cores of these stars, hydrogen and helium could fuse into heavier elements like carbon, nitrogen, oxygen, and so on. The beginnings of our periodic table were finally taking shape. And when these stars ran out of fuel at the end of their lives, they died in spectacular, massive supernova explosions, seeding the cosmos of the products of these stars' labors as they burned out into the night. All elements in our universe, heavier than hydrogen and helium, were made inside the cores of past generations of stars. The astronomer Carl Sagan once said that we are all made of star stuff. And what he meant by that is that the calcium in your bones, the oxygen that we're currently breathing, the carbon, nitrogen, and phosphorus that's in our DNA literally came from the insides of long ago stars. The very beginning of the story of life in our universe teaches us that we are intimately and personally connected to the cosmos. Now, fast forward several billion years, as you do when you're talking about the timescales of our universe, and here we see a new star starting to form at the center of a swirling disk of ancient stellar ashes, of gas and dust. This is something we call a protoplanetary disk. At the center of that disk, a new star is starting to shine. And in the disk itself, surrounding that star, planets are beginning to form from the accreted material, carving out gaps in the disk like grooves in a record. One of these young planets circling this young yellowish star is special. All life, as far as we know, requires liquid water, and this planet has a lot of it. This world orbits in something called its solar system's habitable zone. That's the region around a star where it's possible to have liquid water on the planet's surface. It's where temperatures are not too hot and they're not too cold. They're just right for liquid water. This world might be able to support life. If we now imagine flying to that planet's surface, we see oceans of warm water and small rocky islands starting to form from dark volcanic rocks. In the atmosphere, lightning and ultraviolet radiation from the young star are driving remarkable and complex chemical reactions. Today, we can simulate these same atmospheric conditions and reactions in our laboratory. And in the thick soup of materials that form, we find something amazing. We find the stuff of life. Things like amino acids, the building blocks of protein, and nucleobases, the building blocks of DNA. We even think these compounds exist in the atmospheres of other worlds of our solar system, like, for example, Saturn's moon, Titan. And we've even found them inside of carbon-rich meteorites. It would seem that the building block molecules of life are not difficult for nature to construct. Conditions are just right on this planet for the ashes of those young stars to come alive. And while we don't yet know exactly how the origin of life works, What we do know, at least from Earth's geological record, is that shortly after Earth became habitable, life arose. And so perhaps this tells us that when the conditions are right, the spark of life happens readily. However, all life on this young planet was very different from you and me. It's microbial, entirely microbial. You would need a microscope if you actually wanted to see it directly. And it will remain microbial for billions of years. As far as we know, what I've just described to you is the big picture story of how life can come to be on a planet. Now, there are still gaps in this story that we can't yet fill, but it's fairly clear, at least the outlines of it, based on our current knowledge. But as with all good stories, there's a little bit of a twist here. Because this planet that I've been describing, it looks like Earth, and this story sounds like the story of life on Earth. But this planet, it's Earth-like, but it's not the Earth. And it's orbiting a star that's like the sun, but it's not the sun. This world is something we call an exoplanet, a planet orbiting another star. Many scientists think that the story of life in our universe can be told across many different planets, but we don't yet know how many or which ones. Now, it might be starting to seem like this story that I'm describing to you is a little bit veering on the edge of science fiction rather than science, because after all, I'm starting to talk about alien life, and aliens have a lot of interesting connotations in our society. But this story I'm telling you is not science fiction. In fact, thinking about ways to look for life on other planets is my day job at NASA. But the aliens that I'm thinking about are not so much the little green or pick your favorite color of alien people, but they're more like the friendly little microbes that I was just describing to you. The reason why, when I think about aliens, my mind immediately starts thinking about microbes is because I listen to the story of life on Earth. And what that tells us is that life on our planet was microbial for about 80% of our planet's inhabited history. That's a huge chunk of geological time. And what that might suggest is that microbial life arises fairly rapidly, and maybe it's relatively easy for microbes to evolve. But perhaps it's difficult and takes a long time for complex life to evolve. And I'm not even talking about intelligent life here. So if we want to think about how to detect life on other worlds, what we've learned from the story of life on Earth is that there might be a lot of microbes out there, and we'd better be prepared that the aliens we're finding are going to need a microscope if you wanted to see them directly. So now let's pretend that you were an astronomer and you wanted to observe this planet with your telescope. But this planet is so far away from you that all you can see from it is a pale point of light. If all life on this planet was microbial, how could you hope to detect it from across interstellar distances? Sounds like an impossible problem, right? But here again, life on Earth has a thing or two to teach us. And what it tells us loud and clear is that there's a lot more to microbes than first meets the eye. Because in many ways, life itself is a planetary process, similar to, say, geological processes. And life can modify its environment on a global level. We humans, of course, do this all the time, for better or for worse. But we're not the only life forms on this planet that are able to do this. For example, take something that you're doing right now, which is that you're breathing. And what you're breathing is oxygen. The oxygen that exists in our planet's atmosphere is a byproduct of the dominant metabolism on our planet today, oxygenic photosynthesis. Life can totally transform its environment. And we think that atmospheres on planets with life will look radically different from atmospheres on planets without life. And you don't need complex life to do this. Microbes are really amazing at modifying their environments. For example, when cyanobacteria, a type of single-cell blue-green algae, evolved on Earth billions of years ago and started making oxygen through oxygenic photosynthesis, the composition of Earth's atmosphere was changed forever. The same thing could happen on exoplanets. So if you want to look for life on an exoplanet, and you're not looking for life that's going to be beaming radio signals to you, you could look for these gases in planetary atmospheres that are produced by metabolisms. But how do you do that? So you want to measure the composition of an exoplanet atmosphere. It's not like we can actually send a probe there that's going to sample that atmosphere, at least within our lifetimes. All we have access to are our telescopic observations. So how do we do this? Well, astronomers have an extremely powerful tool in their toolbox, and that's called spectroscopy. Spectroscopy is the study of the interaction between light and matter. All atoms, all molecules in our universe, they all absorb light at very particular colors. We call these absorption signatures, and you can kind of think of them as the fingerprints or barcodes of every compound in our universe. The cartoon behind me is showing the spectrum of the sun. That sunlight, you can see these dark lines interspersed in the bright colors. And those dark lines are caused by absorption of the light by different compounds. So by measuring the spectrum of something, you can learn what it's made of without even ever visiting it. Spectroscopy has told us what the sun is made out of, what other planets in our solar system are made out of, and even what galaxies at the edge of our observable universe are made out of. So you could use spectroscopy to try to measure the composition of the atmospheres of exoplanets. Using spectroscopy, you could split up the light from that planet into a prism to see its rainbow of colors, including colors our eyes can't see, like the ultraviolet and the infrared. And by looking for these absorption signatures, you could find what gases are in those planets' atmospheres. The trick here is you want to find atmospheres that you can't explain without life. And a good example of an atmosphere that you can't explain without life is Earth's atmosphere. The composition of Earth's atmosphere alone is a dead giveaway that our planet is inhabited. And it's been a dead giveaway that there's life on our planet for billions of years, well before we humans got here. The oxygen that we're breathing has been a way that cyanobacteria have been saying, hello, we're here, to the rest of the universe for billions of years. So if you want to find life on another planet, you could look for important gases like oxygen, which I just described to you, and methane, which is another gas that's produced by life. These gases, especially together in a planetary atmosphere, are a very strong signature of life. We don't know of any way for nature without life to make atmospheres containing a lot of both of these two gases. We call these kinds of gases biosignatures. And on a fundamental level, the search for life beyond Earth is a search for remotely detectable biosignatures. We now know that exoplanets, these planets around other stars, are extremely common. In fact, we now know that most stars have planets orbiting them. We've discovered several thousand exoplanets so far, but we know that we've just barely scratched the tip of the iceberg. There are hundreds of billions, if not trillions, of exoplanets within our own galaxy. The universe is literally teeming with other worlds, and the cosmic real estate where life might exist is vast. We also know that the elements or the molecules that life requires, like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, or schnapps, as we like to call them for obvious reasons, are also common in the universe. These ashes from ancient stars permeate our cosmos. Now, a big part of my job at NASA is I'm working on a potential future space telescope concept for a large observatory called LUVOIR, which stands for the Large Ultraviolet Optical Infrared Surveyor. And as you might infer but from the word large in that telescope's name, this is a very ambitious concept. And what I'm so excited about, as far as LUVOIR goes, is that this observatory is being designed to search for biosignatures in the atmospheres of exoplanets. In fact, the title of this talk is The Story of Life in the Universe, and that's also the sort of unofficial motto that we have for the LUVOIR mission concept. So just how big is LUVOIR? Well, this video will show you how big it is. This is from the California Academy of Sciences. Now, what you're looking at right now is the Hubble Space Telescope that everyone in the room is probably familiar with. I love Hubble. Hubble's amazing. And this is LUVOIR, or rather, this is the sun shield on LUVOIR that protects it from overheating. My colleagues always love to joke that this part of the movie, or this part of this video, makes them think of the opening scene of Star Wars. So LUVOIR is really, really big, right? It would be the biggest telescope that we've ever launched into space. And you can get a sense of that from the scale of LUVOIR compared to Hubble in this image. To put some numbers to that, the Hubble Space Telescope's mirror is 2.4 meters in diameter. Astronomers like the metric system. That's about 8 feet in diameter. We're studying 2 architectures right now for LUVOIR, one of which is an 8-meter architecture. It's about 26 feet in diameter, so that's big. And that's not even counting the sun shield, that's just the mirror. And the larger one is 15 meters in diameter, which is about 50 feet in diameter. The reason why LUVOIR is so big is because Earth-like exoplanets are so very faint across interstellar distances. So you need a large light collecting bucket to be able to observe them. The other reason why LUVOIR is so faint is because we don't yet know how rare or common life is in the universe. So by having a large telescope that helps us to see farther and gives us a larger sample size from which to search for signs of life and improves our chances of getting lucky. If life exists on a planet that we could observe with a telescope like this, LUVOIR might be able to find it. And on the other hand, if in this large sample of planets we don't find any signs of life, then that would help us to place an upper limit on the frequency of life on other planets in our galaxy. And either discovery that life is common or life is rare would be profound. We've wondered for so long about whether we're alone in the universe, and a telescope like this would be able to give us some answers, possibly within our lifetimes. The story of life in our universe has taught us that life is intimately connected to the stars, which began to forge the atoms of life, or star stuff, that make up the atoms in our bodies billions of years ago. We then journey to distant exoplanets, these worlds orbiting other suns, which we now know are common in our universe. The question now is not whether exoplanets exist, but which ones are truly Earth-like and how many are inhabited. And we've thought about the life that could exist on these distant worlds, risen from the ashes of long-dead stars just like us. And lastly, we've thought about how to search for signs of life on distant planets by searching for biosignatures in their atmospheres with future space telescopes. The story of life in our universe has transformed our thinking about the cosmos. We humans have come so far that we've been able to trace our own origin story to the stars and the edges of the universe. But inevitably, when we look out at that vastness, we also look inward and we realize how small we are compared to it all. Because while we are citizens of the cosmos, we're also citizens of Earth. And while there may be many habitable planets out there, this one is our own. The story of life in the universe reminds us that we are now the stewards of the story of life on Earth. And it is important for us to take that role responsibly and treat each other with kindness and wisdom and our planet with respect. And while this is now the end of my talk, the search for life elsewhere is just beginning.